In section 9.2, we're going to continue on with what we have started talking about here in chapter 9, and that's power series. In section 9.1, we just looked at a finite power series. We stopped after just generating a few terms. But in section 9.2, we're going to let these polynomials extend out to infinity. And when we do that, there are a few things that we need to be really careful of. So first, let's look at the general format for an infinite power series. Now, if you're ever asked to create one of these, remember we use that Taylor polynomial formula that we talked about in the last section. But just in general, anytime that you see a series of the form, the sum from k equals 0 to infinity times of c sub k times x minus a to the k. This is going to be a power series. We can have any sort of coefficients. There isn't really any rules for the c except that they're real numbers. And we have increasing powers of x, and that's what makes it a power series. So the c sub k's are coefficients. A is the center of the series. Remember, we saw in the last section, we need to identify where we're going to center it at, and sometimes that will make a difference in how accurate our approximation is that we are using this series for. One issue that we run into is that this is going to create a never-ending polynomial because we're allowing k to go to infinity. So this exponent here is just going to continue on forever. And you may remember, you may not remember, so we'll talk about it here for just a second, that polynomials at some point eventually go off to positive or negative infinity. And this is something that's discussed in like a pre-calculus algebra course. The limit as x approaches positive or negative infinity for any polynomial is always going to be either positive or negative infinity. That usually depends on whether the power is even or odd and whether the coefficient's positive or negative. So these polynomials will eventually tend towards either positive or negative infinity. And that could be a problem because if the function that we are trying to approximate with using this polynomial doesn't go off to infinity, that means at some point when our polynomial goes off to infinity, we know that the polynomial is not a good fit anymore. So what we do is we calculate something called the radius of convergence. And it's a fairly complex idea, but the radius of convergence tells us a couple things. It tells us the interval, or with it we can create an interval where the polynomial has finite values we're typically not interested in this polynomial as it shoots off to positive or negative infinity unless we're using it specifically to model another function that's shooting off to positive or negative infinity as well. And where this polynomial is a good fit for the original function. Or a good approximation. Now it may not be, still might not be exact, but it's they stay nice and close. So I want to start off by showing you an example with some graphs. So we're not going to go through how to generate these polynomials, but let's say we've got f of x equals 1 over 1 minus x. If you look at some of the representative polynomials, 0 degree is just equal to 1, first degree is 1 plus x, second degree, is 1 plus x squared, third degree is 1 plus x squared plus x cubed. So you see, every single time I'm just adding on the next power of x. And if we were to go through that whole process we learned in section 9.1 for generating a Taylor polynomial, you would see how we got each of these polynomials. Now, what I want to do is I actually want to graph these and give you kind of a visual representation of what a radius of convergence is. So I'm going to switch over to Desmos here. And our original function is 1 divided by 1 minus x. And then we're going to plot some of the polynomial approximations. So p sub 0 was just a constant function 1. And then p sub 1 was 1 plus x. P sub 2 is 1 plus x squared. P sub 3, we'll do one more. We just add on the next power of x, which would be x cubed. Now that one is in black. Now, if we were to zoom in and we were to continue with more and more and more polynomials, we will see that where these functions go off to infinity kind of scooches in further and further and further. So you can see the last one we did was p sub 3 of x, and that is our black graph. And as soon as it starts shooting off to infinity, we really don't want it unless the function that we're modeling also goes off to infinity. So 1 over 1 minus x does go off to infinity here close to 1. So that might not be an issue, that we go off to infinity here at 1. But the one thing that is definitely an issue is that 1 over 1 minus x, it flattens out on our x-axis as we move to the left. And no matter what polynomial we create, this polynomial is either going to be going off to positive infinity or negative infinity at some point. So there's definitely an issue on the left-hand side of this polynomial. So the radius of convergence, we would have to decide at some point where to cut that function off and say it's no good anymore. It looks like on the right we might be okay because 1 over 1 minus x goes to infinity, and that would be perfectly acceptable. But on the left, we need it to flatten out at 0, and every polynomial, no polynomial we create is going to do that. So we calculate something called a radius of convergence, and that tells us it's going to allow us to create an interval where the polynomial has finite values, if we need it to, and where this polynomial is a good approximation for the original function. So from the example we saw with Desmos, it looks like we're perfectly fine on the right-hand side near 1, but there might be some issues on the left-hand side as we go to x equals negative infinity. So before I talk about how to calculate the radius of convergence, I want to jump back to one of the types of series that we learned in Chapter 8, and that's called a geometric series. These are the easiest to calculate the radius of convergence for because it's built right into the test for convergence. So the standard form for a geometric series was k equals 0 to infinity of a times r to the k. And we said that these are convergent when the absolute value of your r is less than 1. So the reason that's true, if you think about it, r is the value that we're raising to larger and larger and larger powers. If I eventually want this sum to stop somewhere, which is what convergent means, it settles in on just one value, then I don't want a large number here for my r, and then raising it to larger and larger powers is just going to make it grow without bound. So if you raise a number between -1 and +1 to larger and larger powers, they actually collapse in on 0. And that's what's going to make these terms go to 0, and it's going to be what makes the sum stop. So what this means in interval notation is that any r value between positive and -1 should work. We should be perfectly fine as long as we stick within that interval. If we go outside that interval, those r values are going to make this this term here, as k gets larger and larger, it's going to make that term shoot off to infinity, and we don't want that. Another thing to remember from geometric series is that we do have a way of finding the exact sum of a geometric series. If you have it in your geometric series written in standard form, a times r to the k, and as long as your k starts at 0, the sum is always going to be a over 1 minus r. That's almost what this function looks like, 1 over 1 minus x. So if we just compare them, we can say, oh, well, 1 over 1 minus x is just a geometric series with a equals 1 and r equals x. So I can go back in and replace them and say 1 over 1 minus x as an infinite power series is 1 times x to the k, or just x to the k. And that's how I was able to generate the terms of that polynomial so quickly, is because I already knew what the power series for 1 over 1 minus x looked like. So this power series, because it's a geometric power series, it's only good for when the absolute value of x is less than 1. Or, since this is centered at 0, remember the center is what's being subtracted from your x. This means our radius is 1. We're allowed to move 1 unit to the left and to the right of our center, which means we're allowed to stick between -1 and +1 for good results as this polynomial goes off to infinity. So this positive one here makes a whole lot of sense, because if we look back at our graph, 1 over 1 minus x has an asymptote at 1. So we can't go beyond 1, otherwise that wouldn't make any sense. And then it also further restricted us on the left. It said you really shouldn't go any lower than -1. And this is for the infinite series. We just did some terminating polynomials there. So they're saying if you just stick to stopping at -1, you should be good. As we add more and more terms to that polynomial, the polynomial is going to squish in tighter and tighter and tighter, and it's going to be no good eventually at -1. It's going to be shooting off to infinity or negative infinity. So what this radius of convergence tells us is we really need to stay between -1 and +1. Now we could extend this and we could say, well, what's the series for 1 over 1 minus 3x? And if you compare that with a over 1 minus r, that means we have an a value of 1 and an r value of 3x. So you can set up a geometric series, an infinite geometric series for this function, the sum from 0 to infinity of a times r to the k. And both the 3 and the x are part of your r, so both of them need to be raised to the k power. So the times 1 doesn't really do anything, so we could just write this as 3x to the k. And if we wanted the interval of convergence for that function, we would have to say, well, the r value must be less than 1. That's the rule for geometric series. We want x to be all by itself in this inequality because I want to identify what x values I'm allowed to use. So we'll divide that 3 over. That's not going to affect the absolute values there. And we get that x must be less than 1/3, the absolute value of x, which means we've got to stay between -1/3 and +1/3. So as we start introducing larger and larger coefficients there in front of our x, our interval of convergence here is going to narrow. For any other type of series that we might encounter that doesn't match the sum of a geometric series. So here we had something that looked like a over 1 minus r. If it looks like a over 1 minus r, the easiest way is to match it up with the geometric series, identify your a and your r, and go from there. But there are lots of other types of series as well that we can't necessarily match up with a geometric series. So for all other types of series, we're going to use the ratio test to find the radius of convergence. And our goal is going to be to simplify down the ratio test all the way down to something that looks like this. Absolute value of x minus c is less than capital R. And what we have here, c is the center, and if we can get it simplified down to this, that capital R is going to be the radius of convergence. That tells us how far to the left and to the right of our center we're allowed to go and have this infinite series still be convergent. So if we're centered at C and R is the radius is the distance away from the center, we're allowed to move R units to the left of the center and R units to the right of the center. So that's enough information to create our interval of convergence. Inside parentheses, we'd have C minus R as the lower bound and then C plus R as the upper bound. But we have to check these endpoints individually to see if we're allowed to include them or not. We didn't have to do that with geometric series because the geometric series test is very clear. It says R must be less than 1. That's part of the rules of a convergent geometric series, is the absolute value of R must be less than 1. And if it is greater than or equal to 1, then it's divergent. But with the ratio test, there were 3 options. Ratio test, if we're doing looking at the sum from k equals 0 to infinity of any expression whatsoever, whether it looks geometric or not, if we can set up the ratio of a sub k plus 1 over a sub k and do the limit as k approaches infinity, if this comes out to be less than 1, then by the ratio test it's convergent. So that's the one that we're interested in, because we're only interested in figuring out where these geometric series are convergent. But there were some other results we could get from the ratio test. If it was equal to 1, then the test was inconclusive. and that means we'd have to try something different. And if it came out greater than 1, that means it's divergent. We're definitely not trying to find this one. We're interested in when this ratio comes out less than 1. We also need to analyze what's happening when it's equal to 1, and that is exactly the endpoints of that interval of convergence. C minus R would make this ratio equal -1, and then with the absolute values change it to +1, and then C plus R would make it equal to +1. We need to check those endpoints individually to see if we're allowed to use them or not. Inconclusive doesn't mean convergent or divergent. It just means this test can't tell us. So we need to check those endpoints separately. And we do that just by plugging in the values that we get on the endpoints and seeing what kind of series we get. But we'll go through an example with that. So for our first example, we want to find the radius and interval of convergence for the sum from k equals 0 to infinity of 3 to the k, x minus 1 to the k, all over 2k plus 1. This definitely does not look like a geometric series. For a geometric series, we're allowed to have a coefficient and then some sort of x plus or minus the center to the k. So the 3 over k, or 3 to the k over 2k plus 1 will not qualify as a coefficient because it has k's in it. It's got powers of k, and that might be an issue. So the safest thing to do is the ratio test here. And a sub k in our ratio test is exactly what we see inside of our series. So a sub k is 3 to the k times x minus 1 to the k all over 2k plus 1. And then remember, the ratio test wants us to set up and simplify the ratio of a sub k plus 1 over a sub k. So now we need to know what a sub k plus 1 is. And we figure that out just by replacing all of our k's with k plus 1's. So we'll have 3 to the k plus 1 power, x minus 1 to the k plus 1 power, and then 2 parentheses k plus 1 plus 1. And we could simplify that denominator actually and just write it as 2k plus 3. We would have to distribute the 2 and then combine our constants. So the ratio test says start by figuring out the limit as k approaches infinity of your a sub k plus 1 over your a sub k. And these problems start out with just a lot of algebra work. It's typically going to be a fraction divided by another fraction. So one of the very first things we can do to simplify this is, instead of doing fraction divided by fraction, we will flip the bottom fraction and change it to a multiplication problem. So there's our a sub k plus 1, and then a sub k was just 3 to the k, x minus 1 to the k over 2k plus 1. So we will change this into a multiplication by flipping our denominator. And there should be some things that we can cancel. We should have some matching factors in the top and the bottom that we can simplify. You cannot simplify those polynomial pieces, the 2k plus 1, 2k plus 3. So leave those alone for now. But we can get rid of some of the 3's. In the top I have k plus 1 of them. In the bottom I have k of them. Now it doesn't matter what k is. The numerator is always going to have one more. So we can cancel off all of those 3's from the denominator and just be left with 1 in the numerator. And the same thing goes for the x minus 1's. In the top I've got k plus 1 of them. In the bottom I just have k. So no matter what k is, the top is always going to have one more. And we want the limit as k approaches infinity. And let's see what we've got left. We've got 3 x minus 1 to k plus 1 all over 2k plus 3. Now the limit is where we can get rid of these polynomials now, because we can't cancel them because they're two completely different linear expressions, but we can do the limit as k approaches infinity. And if you want to, you could even, this limit is only dependent upon k. So if you want to, you can pull that x minus 1, absolute value of x minus 1 out. That has nothing to do with the limit portion, which is just k's. So we've got 3 times 2k plus 1 over 2k plus 3. Now that limit, because we've got a linear expression in the top and a linear expression in the bottom, the way we do that limit is just by looking at the coefficients. And the coefficient in the top is going to end up as a 6, and the coefficient in the bottom is a 2, which simplifies down to just 3. So if you've got any polynomial pieces, we can't simplify those when we do the flip and multiply. It's the limit that takes care of those for us. So we've simplified it all the way down to 3 times the absolute value of x minus 1. And remember, we're only interested in when this series is convergent, which means I need that limit to come out less than 1. So we ourselves get to say this is less than 1 because we only want convergence. It must be less than 1. So remember what we wanted the format to look like. We want to have absolute value of x minus our center is less than r. And we've almost got that. The only thing we need to fix is that times 3 in the front. So I'm going to divide that 3 over to the other side. So now I've got absolute value of x minus 1 is less than a third. This matches exactly with the format we had said above that we're looking for. So C is the center and R is the radius. If we match that with what we have, we've got a center of 1 and a radius of 1/3. That means I'm allowed to move 1/3 to the left and 1/3 to the right of 1. So I can set up my interval of convergence. We start off with parentheses. If I move 1/3 of a unit to the left of 1, I get 2/3. And if I go 1/3 to the right of 1, I get 4/3. Every x value on this interval is definitely going to make our series convergent, but we need to check what's happening at 2/3 and at 4/3 individually. When x is 2/3, all you have to do is go back to the original series and plug in x equals 2/3. And we're going to simplify it out and see what happens. So the original series was k equals 0 to infinity, 3 to the k, x minus 1, and we're replacing x with 2/3 to the k over 2k plus 1. So let's simplify this as much as we can. 2/3 minus 1 is a negative third. Negative third. In my numerator, I'm multiplying two numbers that have the same exponent. That means you can multiply their bases. When you have two factors with the exact same exponent, you can multiply their bases to combine them. So really in the numerator, 3 times a negative third is a -1. So I've got k equals 0 to infinity of -1 to the k over 2k plus 1. And we want to know if this is convergent or divergent. So we've got to identify what kind of series it is. And there's potentially several different tests we could use on it. Because of that -1 to the k, I'm going to use the alternating series test. Now the alternating series test, we get to disregard the -1 piece. All that tells us is that this is an alternating series. So the a sub k is just 1 over 2k plus 1. There's two things that we need to show for an alternating series to be convergent. The first one is that the limit as k approaches infinity for this expression is 0. And is that true? Is the limit of 1 over 2k plus 1 as k goes to infinity going to equal 0? Well, think about what happens when you plug a really, really large number in for k. Your entire denominator is going to get larger and larger, which means the overall value of your fraction is going to get smaller and smaller. You also might remember from Calculus 1 or from algebra class, anytime that the degree in the denominator is larger, this limit will be 0. The second thing we need to show is that this series is decreasing. And the best way to show that is also something that we learn in Calculus 1. A function is decreasing when its derivative is negative. So I'm going to think of my 1 over 2k plus 1 as a function, and I'm going to find its derivative. And you might want to think of this as 2k plus 1 to the -1. That way we can just do chain rule on it. So this is our a sub k. We're finding a sub k prime. So the chain rule says first take the derivative of your outside piece. So old power comes out front, subtract 1 to get your new power, and then also multiply by the derivative of your inside piece. And I'm going to do a little bit of rewriting. I get -2 over 2k plus 1 squared. No matter what I plug in for k, this answer will always be negative. I know that because my numerator is negative, and my denominator is always going to be positive because I'm squaring it. No matter what you plug into the parentheses there in the 2k plus 1, whether it comes out positive or negative, once you square it, it's automatically going to be positive. So this is a negative divided by a positive, which is always a negative. So we've just proven that our first derivative is always negative, which means this series is decreasing. So when I plug 2/3 in to my original series, I'm able to prove that the series is convergent, which means I want to include 2/3 in my interval. So I'm going to change that parenthesis to a bracket. Before I do any rewriting that, we need to check our other endpoint though, x equals 4/3. And we go through the same exact process. We're going to look at the sum from 0 to infinity of 3 to the k, and then we had x minus 1 to the k. So 4/3 minus 1 is 1/3, all over 2k plus 1. And just like in the last one, since both factors in the numerator have the same exponent, we can multiply the bases. And this is going to be 1 to the k over 2k plus 1. 1 to any power is just 1. So we don't even need to write that as an exponential piece. This is just 1 over 2k plus 1. So that's what the series looks like when we plug 4/3 in. Now we need to decide if that is convergent or divergent. And for this one, I'm going to do the integral test because I recognize this as something that I know how to integrate. The integral test says to integrate from 0 to infinity, exact same bounds as we have on our series, this expression here, but as a function instead. So I just changed my k to an x. It might look a little bit more recognizable that way. So I've got a fraction with a linear denominator. That always integrates to a natural log. You might want to write out the u substitution though, because anytime our x has a coefficient, it's going to introduce an extra coefficient in our answer. So this will turn into a natural log, but we have an extra 1/2 in the front. And we want to evaluate this thing from 0 to infinity. If you plug infinity in, or if you do the limit as x approaches infinity, the natural log graph goes off to infinity. And if you plug in 0, you get the natural log of 1, which is 0. Anytime you do these improper integrals and you still have an infinity in your answer, that means they're divergent. And the integral test says whatever the improper integral does, the series is going to do the exact same thing. So if that improper integral is divergent, that means our series is also divergent. So we do not want to include 4/3 in our interval of convergence. However, we do want to include the 2/3. So our final answer for the interval of convergence is going to be bracket 2/3 to 4/3 parenthesis. We changed the 2/3 to a bracket because when we plugged it back into our series, the series is in fact convergent there. But when we plugged 4/3 in, it was not. So that's why we leave 4/3 as a parenthesis. We don't want to include 4/3 in the interval of convergence. We found that it was divergent at 4/3. So this is a really long process. It requires a lot of algebra skills. It requires you to have all of those convergence and divergence tests from chapter 8 down pat. It also required us to remember something here from Calc 1, that a decreasing function is when the derivative is negative. So that's helpful as well. But in general, these are long problems. Going through that whole ratio test and then checking your endpoints. It's a very long problem.